Welcome to the Quickstart tutorial for AFT Impulse 4.0. This tutorial will teach you the fundamentals of using and understanding AFT Impulse 4.0. Prerequisites include passing an undergraduate engineering course in the analysis of pipe system fluid mechanics, as well as familiarity with standard industry practice in pipe flow analysis. AFT Impulse is a general-purpose tool for modeling pipe network water hammer and pressure surge. Impulse simulates steady state and transient behavior in liquid pipe networks. Impulse implements the method of characteristics for transient surge analysis and optionally the discrete vapor cavity model for cavitation. Impulse can model all liquid systems in which fluid density, dynamic viscosity, and bulk modulus do not change within a single pipe. Impulse can model Newtonian and non-Newtonian fluids using a number of different methods. Impulse can model systems that are pump, gravity, or pressure driven. Some components that can be modeled include a known pressure or flow boundary where conditions can change with time. Various pump models can be applied, including a speed that changes with time, pump inertial effects, centrifugal pumps and positive displacement pumps, and pumps with flow and pressure controllers. Standard valves, control valves, relief valves, check valves, all of these can have a position that changes with time. Gas accumulators, liquid accumulators, surge tanks, and vacuum breaker valves are just a few more components that can be modeled. The engineering assumptions and limitations required to use AFT Impulse include that the wave speed stays constant during the transient simulation, non-condensable gas release is negligible, and pipes are liquid full and fluid is single phase. Alright, so let's talk about the concept of water hammer. Water hammer is a transient phenomenon that occurs in liquid piping systems as the hydraulic behavior adjusts to changing conditions. Water hammer can be caused by many events, including valves opening or closing, pump speed change, relief valves cracking open, tank pressurization, or periodic pressure or flow conditions. Water hammer can occur in any liquid piping system. The term water hammer confuses some because it implies a process only in water systems. This is not true, as transient pressure waves occur in all systems that experience a change in operating conditions, regardless of the fluid. Using AFT Impulse 4.0, you can accurately model transient events throughout your system and review the resultant transient hydraulics. AFT Impulse is broken into 5 primary windows. The workspace and the model data windows are primarily for building and defining your model, while the output, the graph results, and the visual report are primarily for reviewing the results. Let's explore the workspace in more detail. To build a model, you'll be using the toolbox on the left-hand side of the workspace window. This is broken into 4 drawing tools at the top of the toolbox and 19 junctions at the bottom of the toolbox. To place a junction in the workspace, simply click on the junction and then drag and drop it onto the workspace. To draw a pipe on the workspace, simply click on the pipe drawing tool and then draw a line where you would like the pipe to be located. To move a pipe or junction, simply drag and drop it where you would like to move it to. To move one end of a pipe, you can either drag and drop the handle on the end of the pipe, or you can move the connected junction. To enter input data, simply double-click on the pipe or junction and a specification window will open. The specification window is the platform for entering data to define the pipes and junctions throughout your model. To help you identify the minimum required input data, we have highlighted those cells in blue. We will be disabling the blue highlight feature for this Quickstart tutorial in order to make data entry easier to see. To toggle the highlight feature on or off, you can double-click in the background of any specification window. There is a checklist in the bottom left of the screen which indicates what needs to be completed prior to running your model. The red light in the far left will turn green after you're ready to run your model. The solution control and the output control are defined by default for every new model. We will discuss these checklist items in greater detail in a future tutorial. The System Properties window is where you define your fluid data, your viscosity data, and the bulk modulus of the fluid, as well as optionally a vapor pressure for the fluid. In order to fulfill the Define Pipes and Junctions checklist item, you must construct your model in the workspace and fill in all of the required data for each pipe and junction. The section Pipes checklist item can only be completed after all of the pipes are defined throughout your model. The Transient Control checklist item can only be completed after completing the section Pipes checklist item. Now let's dig a little deeper into the toolbox. The pipe drawing tool allows you to draw pipes on the workspace. Keep in mind that every pipe must be connected to a junction at either end. The minimum required input data for a pipe includes a hydraulic diameter, the pipe length, the friction model, and a wave speed. To help you define your pipes, we have provided a pipe material database, which allows you to select a standard pipe material, size, and schedule. The lower portion of the toolbox contains 19 junctions to help you model your system. The reservoir junction acts as a pressure-type system boundary, sourcing or sinking fluid to or from your system. The area change junction acts as a source of reflection for propagating transient pressure waves. This junction balances mass flow, so that all flow into this junction is equal to all flow out of this junction. The valve junction can be defined with either a constant loss factor or with a user-defined transient where the valve opens or closes over time. Now let's build a simple fluid delivery system where one pressurized tank is delivering fluid through a run of pipe into another tank. We will model the effects of closing an actuated valve over different periods of time in order to see how slow we must close the valve in order to avoid cavitation. The system fluid will be liquid ammonia at 75 degrees Fahrenheit. Notice that the system properties are now defined. Now we'll build the model using the toolbox on the left. Notice that as you hover over an icon in the toolbox, there are shortcuts that appear in the bottom of the left pane. If you hold down the Control key on the keyboard, you will be able to draw multiple pipes consecutively without having to re-click the pipe drawing tool every time. Now let's enter input data for the pipes as shown below. All pipes will be standard schedule steel. Now let's enter input data for the junctions. The elevations are shown below. The pressurized supply and delivery tanks are controlled at a pressure of 250 psig, and the area change will be modeled as an abrupt transition. The valve has a full open CV of 1000. The purpose of this model is to identify an acceptable valve closing time in order to avoid cavitation. Let's start with the valve closure time of half of a second. The CV entered here represents the initial steady-state CV for this valve. We're modeling a half-second valve closure, and we're going to assume that the valve closes linearly. Here we can see that the CV of the valve decreases from its initial steady-state value of 1000 to a closed position over half a second. Notice that this transient is set to begin at time equals 0 seconds, beginning from the initial steady state conditions as determined by AFT Impulse 4.0. Now let's rotate junction 4 in order to visually align it with the rest of the model. Notice that the Define Pipes and Junctions checklist item is now complete. At this point, we are able to work on the section pipes and transient control checklist items. AFT Impulse uses the method of characteristics to predict how transient pressure waves propagate throughout the system. In order to apply the method of characteristics to a system, you must set up a characteristic grid in which all pipes can be broken into an integer number of section lengths. The number of sections that each pipe can be broken into can be calculated using the following equation, where A is the wave speed of the fluid in a pipe, L is the length of that pipe, and delta T is the system time step, which is equal to the length of time for a pressure wave to move through a given pipe section. Keep in mind that each pipe section has a computation station at either end, therefore the more pipe sections you have in the pipes throughout your model, the longer the runtime. In order for all the pipes in a system to be broken into an integer number of equal section lengths, typically the section length must be very small. This would require very long runtimes. In order to reduce runtimes, industry standard practice is to allow an error in wave speed to be introduced up to 15%, recognizing that the wave speed is the least certain parameter. The process of setting up a characteristic grid is difficult and complex to perform manually. AFT Impulse's Section Pipes window automates the process of finding the optimal sectioning combinations. Notice that we want 2 sections in our controlling pipe and that we allowed a maximum error in wave speed of up to 10%. As this is a simple model, the maximum error required in order to properly section the pipes is in fact plus or minus 0.2%. Now that we have completed the task of sectioning the pipes throughout the model, we can set up our transient control. The transient control window allows you to fine-tune how the transient simulation will be calculated and saved into output. We will leave all of the defaults set, including the option to model transient cavitation, and change the simulation duration to 5 seconds. Notice that all of our checklist items have been completed, and we are now ready to run the model and review the results. Each new model must first be saved before you can run it. This model has already been saved as Quickstart tutorial.imp, so now we'll run the model and review the results. The output window is broken into 3 sections: the general section at the top, the pipes section in the middle, and the junctions section at the bottom. The results shown here are the initial steady state results. The easiest way to review the transient results is through the graph results window. The purpose of this model is to determine a valve closure time such that we avoid cavitation. The easiest way to identify cavitation for this system will be to plot the vapor volume against the total pipe length. Note that this graph will show the maximum and minimum values that occurred at any time throughout the simulation duration. We can see that there are vapor volumes, and therefore cavitation, present when we close the valve over half of a second. Let's try changing the valve transient to close over 1 second. Although lengthening the valve closure time did not eliminate cavitation, it did reduce the vapor volumes. Let's try a 2-second valve closure. As is shown by the absence of vapor volumes, a 2-second valve closure does not result in cavitation. Now let's animate the transient pressure profile of the 2-second valve closure. Another very useful graph is the maximum-minimum transient pressure profile.